Hi, this is Sudeep Manchanda from Quite Easily Done. This video is a part of this series called Know Your Components, and today we would be talking about OpAmp or operational amplifier. This video would cover what are operational amplifiers, what are the characteristics of an ideal OpAmp, and using of an OpAmp as an inverting and a non-inverting amplifier, its use as a comparator, and also be talking about output saturation. So let's get started. So an op-amp is a direct coupled high gain electronic voltage amplifier which amplifies the differential values the of the signal that is given to its inverting and the non-inverting terminals. So what that means is an op-amp has two inputs. One is the inverting input, which is represented by a negative sign, and a non-inverting input, which is represented by a positive sign. There would be two inputs that would be given to these, and there is an output voltage V, which is an amplified version of the difference of the two inputs that has been given to it. So an operational amplifier actually is, so when we were talking about transistors, we talked of the use of a transistor as an amplifier, and an operational amplifier uses a lot of these transistors. The circuit is relatively complex, and so we don't usually get into that, and we encapsulate the entire circuitries of an op-amp as a triangle, which is the symbol over here representing the two inputs, the inverting and the non-inverting terminal, and the output. In some cases, we also show two other terminals, which are the VCC and the ground, which is the supply to the operational amplifier IC. Now, commercially available ICs for operational amplifiers are mostly the 8-pin ICs, which has 4 inputs, because one IC in that case has 2 op-amp. So 2 inverting, 2 non-inverting terminals, so 4 pins are there for the input, 2 pins are there for the output, one is the VCC and one is the ground. So that gives us the total of 8 pins, and depending on what op-amp you're using in a particular circuit, you can kind of map each of these to that to the pin diagram of that IC. So when we talk of an op-amp, because we're saying it's encapsulated, it gives us inputs and it gives us an output and any other parameter that is there into it, and then it gives us a set of characteristics of how an op-amp would act, so which we call as the ideal the characteristics of an ideal op-amp. Now these characteristics are theoretical it's called ideal op-amp. It's theoretical in the nature that we would talk of infinite and zeros values, but practically they would be nearly equal to that in reference terms, but not the exact same values. But for our understanding purposes, we would consider any op-amp that you are working with being an ideal op-amp. So what are these characteristics? The first characteristic states that the input resistance Ri, the resistance offered at the input of an operational amplifier, are infinite. So which means that the resistance offered at the inverting input and the non-inverting input is infinite, it also means is that the current at the inverting and the non-inverting terminal would always be zero. With such high resistances, the current cannot flow. The second characteristic is that the RO, the output resistance, is zero, which means the amplified circuit, when it is fed to any other electronic circuitries, the resistance at the output terminal would be zero, and the entire current from the output would go to the driving circuit. The third characteristic says that the gain that we get out of an operational amplifier, AV, is infinite, which means the amplification that we get from an operational amplifier is very, very, very high, especially when compared to the voltages at the input and the output. So this might be of the order of 10 to the power 5 times also. The fourth characteristic states that the operational amplifier would try and have the voltages at the inverting terminal, which is V1 in this case, and V2 as equal. So it would do its best, match entire current flows and everything, such that the V1 voltage at the inverting terminal and the V2 voltage at the non-inverting terminal are always the same. The fifth characteristic says that the bandwidth in which the OpAmp can operate is infinite, which means I can give in a signal of any frequency. If it is a low frequency signal, it's going to be very well nicely amplified by the operational amplifier, and so can a very high frequency input signal also. The sixth is that the temperature differences would not cause a drift in the characteristics of an OpAmp, which means that irrespective of if I'm operating the operational amplifier at a 15 degree centigrade or a 25 degree centigrade or a 35 degree centigrade, we would get the same above 5 characteristics irrespective of the temperature at which it is operating. So those are the characteristics of an ideal OpAmp which we would be considering whenever we would be doing our mathematical calculations and stuff. So next, let's talk about a non-inverting amplifier. The circuit that we see is of a non-inverting amplifier. A non-inverting amplifier is one where you would have an input, let's say in this case a sine wave, with an amplitude of 50 millivolts only. Very weak signal. The output would be an amplified version of the same frequency and polarity as the input. In this case, let's say it's amplified around 100 times to 5 volts and negative 5 volts. So a non-inverting amplifier means whenever the whenever the input here is 50 millivolts, the output would also be 5 volts, and when the input is negative 50 volts, the output would be negative 5 volts. What that means is the polarity of the signal has not changed. It's not inverted. So a non-inverting amplifier can also be identified with the fact that the supply voltage of the input voltage Vs is fed to the non-inverting terminal of the operational amplifier, to the positive terminal. Now, we talked of the amplification of an operational amplifier being infinite, which is very huge, is not a very good thing, practically speaking, because let's say I feed in the signal from a microphone to the amplifier, I get a very high amplification, and now this amplified signal I'm trying to feed it to the speakers. Now the speakers can accept or sustain inputs till a particular range only. It cannot sustain very high inputs, right? So we would want the output of the amplified signal to be in the operating ranges of wherever the signal is being fed. That is one reason why you would want to have the amplification less than infinite in a finite range. The second reason what we would is the output saturation. We don't want the output to be saturated. When we look at the simulation of this circuit, we would understand what output saturation is. For now, let's look at the characteristics of an ideal OpAmp, and let's try and do a mathematical calculation to see what would be the amplification offered by this circuit over here. So we know that an ideal OpAmp would give us an input resistance which is infinite. So the current at the inverting and the non-inverting terminal would be 0. What that practically means is the current from the output V0 would just flow through the resistance RF, through the resistance R to the ground, right, which is the current I, and so it's kind of acting like a voltage. It is actually a voltage divider for us, and we can use Ohm's law to come up with the value of the voltage V1 in this case. So we are saying is that the current I in this case would be voltage divided by resistance, which is V divided by R plus RF, which is the total resistance offered by the circuit, the feedback circuit. which also tells us that V1 voltage, which is the voltage over here, which is actually the voltage caused because of the potential drop across the resistance R, would be equal to IR, I being V0 by RF plus R into the resistance, which is R. So this is the value of V1 that we would be getting. Now we said that the voltages at the inverting and the non-inverting terminal would always be the same. Now we can very quickly mathematically actually prove that also, so which I will do in this corner over here. We said that the output voltage V0 would be equal to the amplification AV of the signals Vs minus V1 in this case, right? So we have the supply voltage Vs on the non-inverting terminal and the supply V1 at the inverting terminal, and that is the reason why we are saying it minus V1, because it does a differential. The amplifier would do a differential of the two inputs, which is V1 minus Vf multiplied by the amplification that it provides. Now by that we know that Vs minus V1 would be equal to V0 by AV. Now AV being almost tending to infinite, V0 by AV would be equal to 0, which brings us to Vs is equal to V1. So we know Vs would always be equal to V1. What we would now try and achieve is come up to the value of the amplification that this circuit is providing to us. So amplification A, the finite amplification provided by the circuit, would be the output voltage V0 divided by the input supply voltage Vs. We know this is equal to V0 by V1 because Vs is equal to V1, and from equation 1 of ours we know the value of V1. So the amplification A, which is provided, is equal to R plus Rf divided by R. So all we have done is substituted the values from the equation 1. So this is the amplification that we get out of this circuit, which is the finite values. In this case, the amplification A would be equal to 1k plus 100k divided by 1k, which gives us an amplification of 101. Now this amplification value of 101 we would see in our simulation circuit of being correct. So let's go to the simulation. So here we are on the software which does simulation for us, and this is the non-inverting amplifier. Again, we have the supply voltage Vs onto the non-inverting terminal of the amplifier. Now if we look at the supply, we're saying it's a 1 Hz AC signal for us, alternating, which in this case is sine wave, and the amplitude is just 50 millivolts. Now what we said is this would be amplified 101 times, and what we get is an output V0 in purple over here. If we see, it goes to 5 point something volts in positive maximum to negative 5 point something volts. We look at the input over here once again is this blue thing in the sine wave on the top, and when we look at the output, it's the yellow wave, the same wave but amplified in terms of amplitude. Now in order to better understand what is actually happening, let's convert this to a DC supply of 50 millivolts. So if you see, we are giving now an input of plus 50 millivolts to the non-inverting terminal of the amplifier, and what we are getting out as an output is 5.045 volts in positive as the output. So one, the polarity is not inverted, it's the same as the input. Second, it's amplified approximately 101 times of the input voltage. So in the simulation circuit, we saw that our input signal, which is a sine wave, was being amplified approximately 101 times to give us an output signal which is non-inverted of the same polarity as the input would. Now let's look at a case where we would want the outputs to be inverted as in relationship with the input. So we were now working on an inverting amplifier. An inverting amplifier is where if we have an input which is like this, a sine wave again, we would get an output voltage which would be an amplified version of the same thing, of the same frequency, but a reversed polarity. So this was our input and this is the output. Now how do we know that the circuit that we are looking at is the case of an inverting amplifier? Because the input has been fed to the inverting terminal of the amplifier and the rest of the circuits remain the same. We know from the characteristics of an op-amp, the ideal characteristics of an op-amp, that the current again would be 0. We know that the voltages at the inverting and the non-inverting terminals would remain the same. So over here we see a V equal to 0 because the non-inverting terminal is grounded. So by that we know that V1 would be equal to 0 and there is no current flowing into it. So again, now we have is the same equation where we can now see the current flowing from the output back via the Vs into the ground, and we know that V1 is equal to 0. So let's do the mathematical analysis again to see what is the current flow in this case. So we are saying that the current flow would be the voltage drop across this resistance R, which is Vs minus V1 divided by the resistance R, or it can also be expressed as V1 minus V0 divided by Rf. So which is, we just using the same Ohm's law equation by saying V is equal to IR. So we come up to the value of the current over here. We know V1 is equal to 0. So this comes to as I is equal to Vs minus divided by R equal to minus V0 by Rf. The amplification that the circuit would provide us, which is A, is equal to VO, which is output voltage, divided by Vs input voltage, which brings us to minus Rf by R. In this case, the amplification we are getting is minus 100 kilo ohms by 1 kilo ohm, that is equal to minus 100. The negative sign in the amplification by itself also tells us that the phase of the output will be inverted as compared to the phase of the input. Now let's look back at the simulation and see how this is working. So here is the simulation software. We're looking at our inverting amplifier, where we again have the voltage Vs of 1 Hertz frequency, an AC signal being fed to the inverting terminal of the operational amplifier. This is of amplitude 50 millivolts, and when we look at our output, we see that our output is going up to around minus 5 volts in negative and plus 5 volt amplitude in the positive. And we look at the proper sine wave of the amplified input. So now once again, to understand that what is the polarity, how is the polarity working, we see if I convert the input signal to a DC of 50 plus 50 millivolts, we see that our output has turned red, just to represent a negative sign, and the output V out is minus 4.995, which is almost minus 5 volts, and amplification of 100 times. So the positive input has become a negative amplified output, so it's an inverting operational amplifier. What we can also take the opportunity of the simulation to also see that if I have an AC input of 50 millivolts, I have an operational amplifier with maximum of 5 volts and minimum of 5 volts depending on the supply that I have given it. I see that the output is a proper sine wave, because my peak over here would be 50 millivolts, which would give me a maximum of 5 volts at the output, which is within the range of the op-amp, and so the sine wave comes perfectly. Now let's say my input is a bit stronger and it is of an amplitude of 90 millivolts. In this case, my input is again now a proper sine wave, but when I look at my output, till when the amplification takes the output to a value of 5 volts, it's kind of coming up properly, but then the output cannot go above 5 volts, and if the amplifier is trying to push the voltages to 6 volts, it cannot go. So the top and the bottom of the sine wave is now clipped off. This is what we call as output saturation, where the output is now saturated to plus 5 volts and minus 5 volts in our case, and The amplification does not, the amplified output does not go beyond these values, because of which you're getting a distorted signal. This is what we would want to avoid. There are multiple ways to handle this situation. In this case, one way I have is to change the value of the resistance over here, the RF resistance, to reduce the amplification that I'm getting. Or let's say I need the amplification, all I can do is change the supply voltages to a higher value, which would give me a higher range of output. Now doing this would also mean that I would also have to ensure that the values that I'm entering in right now are within the range of the op-amp itself. So now that I've increased the operating ranges of it, now I'm getting a proper sine wave output again, because now with an input of 90 millivolts amplitude, I'm maximum getting a 9 volt, and I've given the range of plus 10 volts to minus 10 volts to the operational amplifier, so I'm able to get the proper amplified AC signal. So that's an inverting amplifier, and we've also talked of the saturating output saturations. We would now move on to understanding the differential amplifier, which is used as a comparator. Okay, so we have covered the inverting amplifier and looked at that as a simulation, and we've seen that the amplification that we got is minus 100 times for the input. Now let's look at what so this differential amplifier, we would look at its working as a comparator. So a comparator does a very simple job. It checks and tries to give us a logical answer of yes or no for a comparison. Is saying, is V1 greater than V2? So the answer can either be a yes, which is a logic high, or the answer can be a no, which is a logic low. So when we looked at the differential as the amplifier over here, we're saying that it's amplifying the differential values of the input. So what we're getting is V out is equal to amplification of V1 minus V2, which is non-inverting terminal minus the inverting terminal. Practically, the equation we would get is actually AdVd, which is amplification of the differential voltages into the differential voltage, plus AcVc, where Vc is actually 1 by 2 V1 plus V2. So which kind of is telling us that yes, we're getting an output voltage as some amplification of the differential voltage, plus there is other factors to it also. So it's not that a voltage difference of minus 15 millivolt and 50 millivolt, so an amplification of these two input would not be equal to 1050 millivolt and 950 millivolt, just because the difference in both the cases is 100 millivolt. Even then, the output voltage would not be the same because of the component AcVc coming in between. Had it been just V out is equal to Ad into Vd, we would have probably got the same output. So that's just the practical aspect of it. What now we want to understand is what we are doing now is using the concept of output saturation to be able to come up with a logical high or a logic low value of it. So what would happen is, let's say in this case where V1 is equal to 2 volts and V2 is equal to 1 volt, the Vd differential voltage is positive 1 volt. So the output V0 would be a very large number, Ad into plus 1 volt, which would give us a very high positive value, which is close to positive infinite, because Ad is close to infinity, which is not possible because of output saturation. So we would get is V0 is equal to Vcc, positive voltage that we're getting. Let's say that is 5 volts. So we would get an output of plus 5 volts, which is what we are saying is a logic high. So we are saying we are giving a Vcc of plus 5 volts here, and the other terminal is ground. So let's take the other scenario where, let's do that in green. Let's say our V1 was 1 volt and V2 was 2 volts. So what we did before was, because V1 was greater than V2, the comparison was yes, we got an answer of yes, which is logic high. Now when we do this, we again would go with the V output of a differential amplification of -1 volt. Now when we are trying to do that, we're trying to come up with a value of minus infinite as the output voltage, which is not possible. It would go to the lower value over here, which is ground, which would give us a value of V0 as 0 volt, which is a logic low. So we have been able to use our differential amplifier as a comparator to be able to get a logic high or a logic low for our comparison, which says is V1 greater than V2, which is the voltage at the non-inverting terminal greater than the voltage at the inverting terminal. Let's look at this in the simulation software also. So here we're looking at the simulation for our comparator. We said we have a voltage of V1 as 1 volt and the voltage V2 as being 2 volts. So the voltage at the non-inverting terminal, the positive terminal, is greater than the voltage at the inverting terminal. So we get is, so let me make this 0 as we have talked of, and let's say we had a logic. So what we would get in this case is a positive voltage 5 volts, which is represented as a green symbol over it being a positive value. So because the voltage at the non-inverting terminal is greater than the voltage at the inverting terminal, we're getting a 5 volt positive logic high. Let's make it the other way around. Let's say that the voltage at the inverting terminal is higher than the voltage at the non-inverting terminal. In this case, we're getting a value output as 0 volts, which is the logic low. So this is how we're seeing an operational amplifier is being able to work as a comparator for us, and this use of an operational amplifier as a comparator of the two values at the inverting and the non-inverting terminal would be used very frequently in our projects. So by looking at that simulation, we have covered up the final topic for the agenda also. So very quickly, we have talked about what an operational amplifier is. We have talked about the characteristics of an ideal op-amp. We have talked about non-inverting and inverting op-amps. We have talked about the comparators and the concept of an output saturation also. So that is all that I wanted to share about op-amps with you guys. If you have any questions, please let me know about that through the comments section below. If you have any feedback for me, please also share that so that we can improve on. Please like, comment, and subscribe to our channel for more videos. Thank you very much and see you next time.